Good morning. Today will be the last session of energy transport. Okay. So far, we have started with definition of fluxes regarding energy transport, and if I recall, there will be conduction flux, convective flux, and work related to flow work. We put together into the balance, into shear balance, just in the same manner as what we did earlier for momentum to find temperature profile. Okay, I show you several examples, both with conduction only, with convection, with flow work. Okay, and then we generalize the shear balance into the equation, so that the equation that we obtain, which is called equation of energy, can be applied to any problems. I show you several examples using that equation of energies together with Navier-Stokes equation in momentum transport, okay, last time. Now, the last part of the session will be interface, the consideration of the heat transfer near interface between fluid and solid, okay? In the text, there will be a part regarding the heat transfer in turbulent flow and heat transfer in more than one dimension. We will neglect that part and skip to the chapter 14 of Bout, Stewart, Lightfoot textbook, which would be about interface. Okay, and this part would be similar to the interface that we study in momentum part, in the sense that during that time we define friction factor, so that friction factor can be incorporated into macroscopic balance and can be done easily if you do the macroscopic balance. But friction factor itself would be determined by microscopic balance. Okay? So in the same manner, for energy balance, to make things easier for the calculation in macroscopic level, at first, just like these examples, this is heated wall and air, cool air as an ambient air, okay? If the high temperature of the wall is T1 and temperature of air is T2, we discussed that the temperature profile, the actual temperature profile would be something like this. It would be nonlinear. And the fact that I showed this graph to be nonlinear means that I already incorporated the convection term, okay? Because if it is conduction only, the curve for one-dimensional heat transfer is supposed to be linear. This is nonlinear. So therefore, there might be natural convection outside of the air here. There might be forced convection of the air out there to remove heat from the heated wall and giving us the nonlinear curve. And of course, we have learned that convection or calculation regarding convection is really, really complex. So in order to make things easier, Newton's law of cooling, or Newton, proposed the simplification by set up one layer. This is called film resistance. And this layer would be considered, this is film, okay? It would be considered as a stagnant layer, and heat would transfer through this layer by means of conduction only. That means in this part, there is no convection at all. So therefore, the temperature profile in this region would be purely conduction. The temperature profile in this region would be linear because the heat transfer is purely conduction. And the rest, outside here, there will be no disturbance in temperature profile at all. So temperature remains constant throughout the rest of the air. This part is called bulk. Okay? In the bulk, it is assumed that nothing changes with respect to position. That means temperature, properties, any other properties like viscosity, density, or even velocity is not function of position in bulk region. Okay? And therefore, after that, using this, we can calculate heat flux as heat transfer coefficient times delta T. This is called Newton's law of cooling. And heat transfer coefficient is supposed to be calculated or supposed to be determined by means of experimental setup. All right? Now, in this Newton law of cooling, delta T is supposed to be put there by the user, and you have to realize that delta T is supposed to be high temperature subtracted by low temperature. You have to put the direction of heat transfer by yourself. Okay? But in this Newton law of cooling, in this particular problem, delta T would be T1 subtracted by T2, which is exactly the driving force of heat transfer. Because right now the problem is simplified to be conduction only. This is T1, this is T2. The difference in temperature would be a driving force of conduction. So this is called driving force for our calculation. But as a chemical engineer, in the heat transfer problem that we will see mostly, that will be heat transfer in the pipe, because normal heat exchanger is constructed as a collection of pipes. If you are taking unit operation 3, at the moment you see we have several kinds of heat exchanger. For instance, double pipe heat exchanger or shelf and tube heat exchanger. All of them contains pipe. Okay? So in this case, if we want to calculate heat transfer within the pipe, from, let's say, if this setup, I have fluid or liquid flowing in the pipe, and there's some means to heat the fluid from outside. That means I have heat transfer from outside into the fluid inside the pipe. So if I have a flow of water with some temperature going in, I want to heat the water up. Outside at the outlet here, temperature is supposed to be higher. Now, if I want to use Newton law of cooling, so that the calculation will be easier, I do not want to get complicated by the calculation of convection. If you realize this is forced convection problem that we have done before, and you see that there will be differential equation that is very, very complicated. Okay? So in this case, if I want to use Newton law of cooling, I have to draw out the foam resistance. So this is foam resistance. Okay? So in this case, the driving force for heat transfer through this foam resistance is supposed to be temperature at the bulk or at the interface between bulk and foam. For instance, if I'm looking at this position, the driving force, the actual driving force, is supposed to be difference between temperature at this point and temperature at the wall. All right, just like in that picture for the heated wall. So this is my wall. This is the wall. And this is the foam. This part is the foam. This is the wall. And inside here, this is considered bulk. Okay? So somehow I have to calculate heat transfer through this foam. The problem is, if you look at the system, now you see that the temperature of the bulk, in this case, if I plot the temperature, let's say at this position, plotted R from center to, let's say, the radius of the pipe. The problem is heating, so temperature at the center is supposed to be low. Temperature at the wall is supposed to be higher. Okay? And you should be able to guess that the temperature profile here will not be linear. So temperature profile, that's supposed to be non-linear. Let's say temperature profile will be something non-linear. Okay? If it is non-linear, you see that temperature is depending on radius. All right? Unlike in this problem, unlike in the heated wall, where temperature of the bulk in this area is constant. It does not change with respect to position around here. But in this case, even though I'm saying that this is the wall, this is the foam, okay, this is the foam, and you see that temperature around here, which is considered bulk, is not constant. It's changing with respect to position. That's one problem that we have. It's not so simple as the conventional heated wall. On the other hand, you see that at this position, at the inlet, temperature would change like this. At the outlet, if I plot another graph as 0 and capital R, let's say temperature of the wall remains constant at this position. This is the wall, this is the foam. If you compare at the center, temperature of the water at the center once is being heated through the pipe, on the pipe, okay? You see that eventually at the outlet, temperature should rest higher than at the inlet. So your temperature profile would now look like this. It's not as different as in the inlet anymore. So that means right now my temperature for the whole system supposed to be a function of R and Z. The problem that we have temperature as a function of R means that we will have a problem defining what is called bulk temperature. The problem that I have for T being function of Z, that means my driving force for heat transfer is changing with respect to length of the pipe. That's also very complicated. Okay? The third complication is that in order to do the calculation of the heat flux or the heat transfer from outside in or inside out, you have to realize if the driving force is changing with respect to the length, that means amount of heat transfer should be changing. In order to calculate that, you have to know exactly the difference. You have to know exact difference of the temperature at every point. But in reality, there's no way that we can put the temperature probe all the way at every point in the pipe, because sometimes the pipe is not the pipe by itself. The pipe stays within another pipe. It's in closed vessel, so there's no way we can measure the temperature. So that's the third complication. Okay? We would prefer to do the calculation so that we know heat going in and out throughout the whole system just by calculating from the inlet and the outlet. So basically we want to do macroscopic balance, but somehow we have to use the information from microscopic balance to incorporate the calculation. Okay? So the first problem, let me say it again, the first problem is that the bulk temperature is not linear, it's not constant, it depends on the temperature. The second problem is that the driving force is changing with respect to length. The third problem is that we cannot really measure the temperature itself, even at the wall. Okay? So, to solve the first problem, the problem about non-constant bulk temperature, we can make another definition for the bulk temperature, let me call TB. Okay? TB here would be bulk temperature, can be approximately from what we call cup mixing temperature. What is cup mixing temperature? Let's say you have hot water going out of the pipe here, and you have to realize that temperature at the center and temperature near the wall are not the same, they're different. But if you somehow take the water here, collect them in the cup, and stir them constantly so that temperature of liquid within this cup will be uniform. This is definition of cup mixing temperature. Okay? Mathematically, cup mixing temperature can be calculated based on velocity and temperature, because at the center, liquid flows at high velocity. Near the wall, liquid flow at lower velocity. So if you collect this liquid for, let's say, 1 minute, majority of liquid, more liquid would come from the center part, and less liquid would come from near the wall. So temperature would be lean toward the center. Okay? So in order to find the average value, you need to incorporate velocity as well. So by definition of cup mixing temperature, you need to find average of velocity times temperature divided by average velocity. This symbol represents average. Okay? So mathematically, it means that you have to integrate, do the double integration of velocity Vz times temperature. Okay? And since you do the integration across the cross-section area in cylindrical coordinate, you have to integrate it with R. This R would be a product integration by calculus. Okay? Integrated dr d theta. When you integrate it with respect to dr, that means you integrate from center to the wall. When you integrate it with respect to 2 theta, that means you integrate for all angles. That's eventually, for this double integration, you try to find the average across this cross-section area. Okay? So R would go from 0 to R. Theta would go from 0 to 2 pi. That's the numerator. For the denominator, it's basically average velocity, Vz times R. This is the part of calculus, dr d theta, from 0 to capital R and 0 to 2 pi. That's the definition of cup mixing temperature. Okay? So if somehow you can do the calculation, let's say we can do that. That means my cup mixing temperature can be approximated and now from the actual temperature profile that is nonlinear like this, I can find some certain value of cup mixing temperature. Let's say this black line. So from the center to the temperature near the wall, I do the calculation of TB. Of course, TB cannot exceed these two limits. It has to stay in between. So if TB is around here, let's say this is TB, okay? So I can say that now, from now on, I would assume that whatever inside the bulk has the same temperature until it reaches the interface between bulk and film. And within the film, it stays as linear temperature profile, just as what we did in heated wall. Okay? So within the wall, there will be conduction only, and temperature profile becomes linear. Outside the wall, for the bulk, temperature remains constant. So that's our first approximation. Of course, if you do the calculation of TB at the other position of the pipe, you get another value of TB. And let's say this is TB at the end of the pipe. And then you get this picture. All right? So now you did handle some problems already. So the first problem, that T is a function of R and bulk temperature is not constant, is changing with respect to position, has been dealt with by calculating bulk temperature. But again, you have to realize that bulk temperature now is still function of length. This bulk temperature at the inlet and bulk temperature at the outlet are not the same. Okay? Now, if I want to do the microscopic calculation to find amount of heat transfer so that I can heat fluid from cold temperature to high temperature, okay? So if I neglect conduction in Z direction for the moment. We have proved that in this kind of forced convection, conduction in Z component is negligible compared to convection. Okay? Right now we have conduction in R and convection in Z direction. So I can assume that once I already find my bulk temperature, so that everything across the cross-section area supposed to have temperature near bulk temperature. So let's say if this is my slice, and this is dotted line representing foam. Okay, so outside here, that would be my foam. Inside this area, temperature remains uniform. It's not function of position anymore. And temperature here would be my bulk temperature. So if there is a heat transfer from outside into this slice, all right, of course, temperature going in is supposed to be lower than temperature going out because you supply some heat and this amount of fluid is heated up. So if I look at this position, I get the wall. This is my foam. This is foam. This is wall. And out here, it is bulk temperature. The temperature of bulk is TB. The temperature of the wall, let me call this one T0. Okay? So for this small slice, I can do the calculation using Newton's law of cooling. So if I use Newton's law of cooling, let's say Q equal to heat transfer coefficient times delta T. And this delta T would be temperature of the high temperature subtracted by low temperature. Right now, heat is transferred from outside in because wall at higher temperature. So if I say T0 is greater than T bulk, so my delta T would be T0 subtracted by T bulk. Okay? Now, of course, right now the flux is local because the slide is very thin. So instead of representing in terms of the flux, I would prefer to say this one is heat flow. But this heat flow is flow within very small slice. So you can say that Q is equal to the flux times the area. Okay? So if capital Q here, let me put it this way. Capital Q supposed to be small q times area. And small q is H delta T times area. This area is supposed to be heat transfer area. And right now, heat transfer area would be this surface area of my slice. Okay? So if the diameter of the pipe is D, the surface area here would be pi D, which is circumference of the pipe, times dz, if the width of this slice is dz. Okay? So I have Q, which is H delta T. I put H already, so I put delta T here. So that would be my heat transfer into the slice. Of course, right now, because the slide is so small, I would say that the Q would be small part of the whole length. I put D here just to say that this part is a differential part of the heat from the total pipe, for the whole pipe. Okay? Now, in order to find the overall heat transfer through the whole pipe, require to heat the water from this temperature to that temperature, I need to do the integration of this equation. If I do the integration, I end up with total heat, right? And integration means that I move this slice from the very beginning throughout the end, just like what we did earlier. Okay? Now, this is one approach. If you do the microscopic equation balance, microscopic balance, why I call this one microscopic? Because we start from small slices and we have to integrate them from the very beginning to the end. This is microscopic approach. On the other hand, if I want to do macroscopic approach, I just look at the inlet and the outlet. Okay? If I say the inlet would be one plane, the outlet would be the second plane. Okay? The balance is supposed to be done from the inlet and outlet only. That can also be done. But, of course, as I said, my problem is that if you want to do microscopic balance, we cannot measure temperature at each point. What we prefer is to represent the whole amount of heat transfer for the whole pipe by means of simple Newton law of cooling. But now the delta T that we are going to use, instead of using exact driving force, we are going to use the temperature from the inlet and the outlet somehow. Okay? So people have defined the way to do that easily. So this is defined or definition. Okay? One simple definition, which might be confusing, is that the whole amount of heat transferred for the whole pipe can be calculated using Newton law of cooling, in the equation in terms of Newton law of cooling, HA delta T. Okay? This is in form of Newton law of cooling, but it is done macroscopically. Okay? So that means this T is supposed to be temperature from the inlet and outlet. Let me write down the same equation here for the moment. All right? The easiest way that you might understand is basically use A, this area, is supposed to be the area of the whole system because we are doing macroscopic balance. So the area of the whole system would be pi d, which is circumference of the pipe times the length L. Okay? So I'm doing the whole pipe balance. And the easiest way to understand is this delta T can be used by using T01, which is wall temperature at the inlet, subtracted by Bout temperature at the inlet. So this is driving force at the inlet, right? But using driving force at the inlet alone seems weird because the whole pipe, heat transfer is done continuously throughout the pipe. So we need to somehow find the average value of the driving force. So in order to find it easily, basically you just do the arithmetic means. So this is driving force at the beginning of the pipe. I'm doing the same at the end of the pipe. T02, that's the wall temperature at the end of the pipe, subtracted by TB2, which is bulk temperature at the end of the pipe. So this is driving force at the beginning. This is driving force at the end. You add them up, divided by 2. So that the whole thing here is average driving force. Okay? So this is called delta TA, where A means arithmetic mean. Okay? So this delta T would be arithmetic mean of terminal temperature difference. Okay? So still, I still rely on Newton law of cooling. I still rely on driving force. But now I used average driving force throughout the pipe. That's one way to do the calculation. Okay? The other way, if you already learned the heat exchanger, you will be more familiar with this equation. Same form, delta T, but changing from arithmetic means to logarithmic means. Okay? So if I do that, then it will be equal to heat transfer coefficient times area. Now this driving force would be averaged by means of logarithmic means. So it is still driving force difference between temperature from the wall to the bulk, but the way to average is now being logarithmic. Okay, this is the way to do the logarithmic means. Instead of finding arithmetic means, the regular arithmetic means, this is logarithm. So if this one is logarithm, this is delta t log mean. Okay, either way you can do that calculation. All right. Now, if you look at this equation, you see that area for both of these would be the same, but delta t would be different. In order to get the correct Q for these two sides supposed to be the same value. So that means heat transfer coefficient in this case must be different. Okay? In this case, for arithmetic means, I'm going to say this one is called HA, and this one will be called H log mean. Now it relies on the same Newton law of cooling, but this is done macroscopically. Now there's the third one. The third one is here, okay? Doing the same thing. I use heat transfer coefficient, pi dl, which is area. But now this delta T, I am going to use T01 subtracted by TB1, which is the driving force at the inlet only. So it seems weird, doesn't make any sense that we can calculate heat transfer to the whole pipe using the driving force at the inlet only. This is, you have to realize, this is the simplest way to do it, even though it would be the worst option. But I'm going to keep this one up because it is easier to do the calculation, and I will show you later on. If you use this case, this is called inlet. Heat transfer coefficient, so this one will be H1. Calculate at the inlet only, and delta T will be called delta T1. This is HA, this is H log mean. All right? Now, once we compare, we set up microscopic approach, we set up macroscopic approach, all this heat calculated in either way is supposed to be equal. Of course, right now, since we are in transport phenomena, we have to say that this approach would be correct one, of course, right? Because for macroscopic balance, at this moment, we do not know how to obtain H value. According to formula, of course, it would be correct, but it's still missing the way how to find H. So in order to make things a little bit more harmonious, we need to find H from microscopic balance. That's why this chapter is called Interphase heat transfer. We do microscopic balance and somehow link this one to macroscopic balance. Okay? So I'm going to show you this way to do the comparison using an example. Example is, I have a pipe, there's water going in, temperature, bulk temperature in is TB1, temperature going out is TB2. Now, to make things a little bit easier, for this particular example, I am to set up the surface temperature or wall temperature to be T0 uniformly throughout the pipe. Okay? How can we get uniform temperature in real life? Basically, if I put this in, let's say, boiling water doesn't matter whether inside the pipe what kind of temperature you have. If the water is boiling, temperature outside the pipe would be 100 degrees C everywhere, right? That's the way we control the temperature of the wall to be constant. So if I put this pipe in boiling water, I put cold water in here, water will be heated up throughout the pipe. And you have to realize that at the inlet, this water is cold. So therefore, difference between temperature inside and the temperature of the wall would be large. So heat transfer here at this location is supposed to be large. Outside here, water is already heated up. The temperature is higher than that. Of course, the change in temperature between TB and T0 would be small. Driving force for heat transfer here would be small. So along the pipe, there will be heat transfer all the way, but it becomes smaller and smaller. So that means driving force for heat transfer now depending on Z direction. All right, this is our setup. We want to calculate the total amount of heat transfer through the whole pipe. So if I do microscopic balance, that means I select one slice with the thickness dz, and amount of heat transfer into this slice is dq. So note that dq should be equal to flux times the area of this slice. Heat transfer area will be pi d dz. And since we are going to move this slice from the very beginning to the end, the amount of heat would vary according to what I wrote over here. Heat flux is vary with position. So to make things clear, I would say this one is flux local. This is local heat transfer. Okay? So if I do the shell balance, I neglect conduction term in Z direction. I neglect kinetic energy, okay? Because there's a change in temperature. As I said from the last lecture, whenever you have temperature change, internal energy would change and internal energy would be dominating. You can neglect kinetic energy. If I neglect work, flow work, let's say I'm saying that velocity is not so fast, viscous heat will be neglected. I can do the energy balance from the inlet and outlet of this shell. Okay? So if I'm doing shell balance here, I would get energy going into the shell would equal to mass flow rate times heat capacity times TB. If this side is TB at Z, that side would be TB at Z plus delta Z. So inlet, I have TBZ. Of course, this looks like thermodynamics because this is heat capacity times T. But actually in thermodynamics, you're supposed to have delta T here. But normally in thermodynamics, we said 1T subtracted by reference temperature. Okay? And reference temperature can be any number. In this case, I'm going to set reference temperature to be 0. So mass flow rate times heat capacity times delta T, and this reference temperature becomes 0. This is energy in, all right? Minus energy out, which is WCP TB at Z plus delta Z, plus heat transfer from outside in. So this is conductive heat transfer from outside in here. So that would be dq. And my dq is basically small local flux times the area pi d dz. That's equal to 0 at steady state. Okay? Now, if I move these two terms to another side of the equation, I would end up having this part first subtracted by this part. On the other side of the equation, I will have this term. So let me write this term again. Q local times pi d equal to, on the other side, I have WCP. Okay? And I have TB as Z plus delta Z first, subtracted by TB as Z. And I divide the whole equation by dz. Or let's say this one is delta Z to make things easier. Delta Z. Okay, just make it similar to what we did in chapter 2 or chapter 9. So if I divide this by delta Z and take limit of the whole thing, limit delta Z approaching 0, these terms turn to be differentiation. So this would equal to WCP dTB by dZ. All right? So from this, I can move dZ to the left-hand side. And I get Q local pi d dZ equal to WCP dTB. Okay? This is my microscopic balance. All right? Now, I will reserve this board for macroscopic balance, so I want to remove this. All right. So now once we get this one from the shell balance, we want to link this equation to Newton's law of cooling. Okay. From earlier, we said that locally, Newton's law of cooling is defined based on this equation, dq equal to heat transfer coefficient times the area, which is pi d dz. This is small heat transfer area of the slice, times delta T, which is exact driving force. In this case, heat would be transferred from outside in. Driving force would be outside temperature subtracted by inside temperature. Outside temperature is constant at T0, subtracted by inside temperature. We call this one TB. Okay? And since at the very beginning I say this one is local, so to make things consistent, I'm going to say this heat transfer coefficient is called heat transfer coefficient local, local heat transfer coefficient. So this is definition, according to Newton's law, is heat transfer from the outside of the slice into the inside. All right? Now, I want to tie this one to the balance equation that we just got. So this, if you take a look at this part, this is Q local pi d dz. This is the same as that. So I can say this part is being dq. And this dq can be replaced by this whole part. All right? So if I write this part first, I get h local times pi d dz T0 subtracted by TB. Okay, so this is dq here, equal to this part, WCP dTB. If I rearrange the equation, I will end up with H local being WCP over pi d 1 over T0 subtracted by TB dTB by dZ. All right? So I'm going to keep this one in mind for the moment. This is local heat transfer coefficient for this particular example. All right? Now on this side of the slides or this side of the board, it is microscopic approach. So I'm going to do macroscopic approach on this board. This one would be macroscopic. So macroscopic balance, that means I'm doing balance in and out. Okay? So basically it is energy balance in is equal to out as steady state. Input, first I have heat going in throughout the whole length. So all the fluxes will be combined into net heat. The total heat will be Q plus energy that fluids carry in. The cold fluids, even though it is cold, it carries some energy. So this energy is being WCP TB1. All right, this is energy carried in by inlet flow. For outlet flow, it will be the same WCP, but temperature becomes TB2. So this is in is equal to out. From this equation, if you rearrange, you can get Q equal to WCP TB2 subtracted by TB1. Okay? Of course, if you look, outlet temperature is supposed to be higher than inlet temperature because the system is being heated up. Right-hand side, this term will be positive. Q is positive. That means system receives energy. So everything is correct here. So if I use, let's say by definition, let's say if I use HA to make it a little bit understandable, HA, Q would equal to HA times A, which is total heat transfer area, pi dL, times delta TA. Okay? So if I use arithmetic means heat transfer coefficient, I have to follow this equation. This is Q equal to this side of the equation, WCP TB2 subtracted by TB1. Okay? So I'm replacing Q by definition of heat transfer coefficient. If I rearrange the equation, I will get HA equal to WCP over pi D TB2 subtracted by TB1 over delta TA. Now, even though I have only one single D here, I want D over here, so I put D squared down here and L. Okay? Similarly, you can change this HA into H log mean. It would be different definition, right? So H log means times A, which is pi dL. This would be delta T log mean equal to the right-hand side remains the same. WCP TB2 subtracted by TB1. Now if I rearrange, I get H log mean in the same manner. The only difference would be down here would be delta T log mean, and this would be D over L. All right. Now I want to compare the heat transfer coefficient from macroscopic balance to what we define from microscopic balance, but the form of equation will be a little bit different. So I want to go back to this part to make it a little bit similar. All right. Now, I have T0 subtracted by TB over here, dTB over there. I have dZ on this side, but on the other side for the macroscopic balance, I have L. So if I change dTB into D of the whole thing here, so that would be the logarithm of T0 subtracted by TB. I can also change dZ into D of Z over L, okay, using calculus. If I do that, I will get WCP and minus up here divided by D squared D ln T0 subtracted by TB divided by D of Z over L. I'm doing this simply because the process of changing this differentiation, I would end up with D over L over here. And that, now we have D over L. Let's say this is D over L. I have D over L over here. I have D over L over there and there. Okay? So if I plot between H and D over L for both microscopic and macroscopic balance, so basically I plot between H versus D over L. And I do actual experiment measuring everything else. Okay? Set up mass flow rate, use heat capacity, measuring temperature at different positions, and try to come up with heat transfer coefficient local, heat transfer coefficient by means of arithmetic means, logarithmic means, and plot like this. So I should have the red line somehow for H local, and the blue line, whatever it would be, for HA, and another one for H log mean. And of course, if you do it for the complete set of equation, you have the third one for H1, for inlet means temperature. Okay? From the real experiments, people have found that these two, H log mean and H local, are closely related. So they're similar in form of shape and location and position. So therefore, people always said that H log mean would give better or more accurate calculation than HA or H1. That's why when you do the calculation for heat transfer in heat exchanger, you usually use H log mean. Okay? Now, once we set up that, of course, from the very beginning of this class up to this point, we have defined several ways to find heat transfer coefficient. We have somehow used neutral law cooling for macroscopic balance to assist the calculation to make things easier. And eventually, we found that using H log means is the best option. All right? So next is how to calculate H itself. Okay? So the last part of this chapter is dedicated to how to calculate this heat transfer coefficient. And I'm going to show you using another example. Now, this set of example is what we did in chapter 11. And I will write down in the same manner. It's still forced convection in the circular pipe. Heat will be transferred from outside in. There'll be water flowing in. Okay? But for this particular system, the flux should be constant. This is constant flux. The word constant flux means flux at the inlet on the middle part of the pipe, and at the end remains the same. So in order to get the constant flux, that means temperature of the wall at the very beginning supposed to be small, and at the end supposed to be large to keep the driving force constant. Okay? And from chapter 11, if you set up equation of energy together with Navier-Stokes equation, I show you that you will end up with this equation, with this partial differential equation, that convective transport in z direction would equal to conductive transport in r direction. This is what we got from chapter 11. Okay? We also got this part from chapter 10 as well. In chapter 10, we end up with another term, conductive transport in z direction, and viscous heat. We ignore viscous heat because velocity is not so fast. We ignore conduction in z direction because we said that in z direction, convection is dominating. Okay? So at the end, we end up with this. During that time, I said that this one is complicated. I did not want to show you how to solve the equation. I just asked you for the boundary conditions. All right? So, actually, if you want to solve this part, there's no analytical solution if you consider the initial part of the pipe. The only solution that is available would be at the end of the pipe, when z is very long. Okay? So if z is very long, there's a way to do the calculation here to get the solution. And I do not want to go through that. I just want to give you the solution right now. If the temperature of inlet water is T1, all right? Now, from here to there, it requires maybe 5-6 pages of the calculation. At the end, you get this function. Basically, it's temperature. There's a temperature here. So there's temperature here. So this is basically temperature. As a function of A, which is Z, this is Z, and B, which is R. Okay? It means temperature profile depends on Z and R. Of course, right now, this is supposed to be toward the end of the pipe, not very beginning. Okay? And this weird number, 1/4, 7/24, that was obtained by applying boundary condition. Okay? Just saying that this is what we set up, this is what we got from here to there, that's calculus. Okay? The point is, you will call this one temperature profile. Just like in chapter 6, we got velocity profile, and from that velocity profile, we can calculate friction factor. Okay, so from the data obtained from microscopic balance, we get the things that we can use for macroscopic balance. We are doing the same thing from temperature profile. We are going to define heat transfer coefficient, and that heat transfer coefficient will be used for macroscopic balance. Okay? So from here, from this temperature profile, if I want to find wall temperature, okay, wall temperature occurs at R equal to capital R. And R equal to capital R makes B equal to 1, right? This B is R over capital R. If this is wall, this small r becomes capital R, and B is 1. So if I replace B equal to 1 in this temperature profile equation, I will get temperature, or this complex function of temperature, equal to 4A, which is Z plus 1 minus 1/4 minus 7/24, which is 4A plus 11/24. All right? So I'm using the calculating results to find the value of temperature at the location that I want. Of course, this is location at the wall. It's still a function of length. A is function of Z. So you should note that it is still function of Z. So this wall temperature is changing with respect to length. Okay. So if I translate this phi back to temperature, on the left-hand side, I can get T minus T1. And now, temperature here is wall temperature, and I always call wall temperature T0. Of course, you have to realize T0 here is changing with respect to Z. Okay? That would equal to 4A plus 11/24 times Q0 R over K. All right? In other words, I can move T1 from here to this side. That will be my wall temperature. And I want to make sure that you understand that this is function of Z. Now, same thing. From temperature profile, I can find bulk temperature. Bulk temperature is defined by the average with respect to velocity. This is definition of cup mixing temperature, which we will use as the bulk temperature. Okay? And basically, you take this temperature profile, do double integration over the cross-section area, divided by average velocity, and from here to there, that's calculus again. I just want to give you the solution. That should give you T1 plus 4A times Q0 R over K. Okay? Now, once we have wall temperature, which is higher than bulk temperature, if I take this pair, that's my driving force. Okay? So if I take first equation, second equation, I take 1 subtracted by 2. That is my driving force for heat transfer locally. So I would get T0 subtracted by T bulk equal to the whole thing here, 4A plus 11 over 24 Q0 R over K plus T1, this is T0, subtracted by T bulk, TB, T1 plus 4A Q0 R over K. Okay, and you see that 4AQ R over K here and there cancel out. T1 here and there cancel out. What we have left would be 11 over 24 Q0 R over K. And in macroscopic balance, we do not prefer R, we prefer diameter. So that would be 11 over 48 Q0 D over K. Okay? Now what I'm doing, I'm finding driving force for heat transfer at different positions. Now you see that heat source has temperature depending on Z. Inlet or inside the fluid, bulk temperature depends on Z as well. But for this particular example, the driving force remains the same. In this side of the equation, there is no Z at all. Inside here, there is no Z. What does it mean? It means that driving force is no longer a function of Z. That is consistent by the fact that I said earlier, in our system, heat flux is constant. To make heat flux constant, driving force is supposed to be constant. And the word constant means it's not function of position. Okay? So at this point, once we get driving force to be independent from the length, it means we got it right. Okay? Now, from the definition, Q local equal to H local times driving force. That means my H local would equal to Q divided by T0 subtracted by TB. If you look at that part, this is definition. From the calculation, if you rearrange the equation, I can get Q0 by itself. The rest would go to the other side. So Q0 from the calculation will be 48 over 11 K over D T0 subtracted by TB. Okay? So this part is basically obtained from temperature profile. Okay? We calculate flux from temperature profile. And then we tie these two together. This is definition. So that means our local heat transfer coefficient can be calculated by equaling these two equations. So delta T would cancel out, and I can get H local to be 48 over 11 K over D. Okay? So this is how we calculate heat transfer coefficient based on our temperature profile. So from temperature profile, which was obtained microscopically, we can get this variable that can be used in macroscopic balance. Okay? To make things a little bit more universal, people would try to define dimensionless variable. This one is called Nusselt number from H D over K. If you look at the unit, heat transfer coefficient is supposed to have unit of watt per meter square Kelvin. Okay? You can look at this equation. Q would be watt per square meter. This is Kelvin. So H would be watt per square meter Kelvin. Diameter would be meter. K itself, thermal conductivity, would be watt per meter Kelvin. And then all units cancel out. That means Nusselt number is dimensionless. So it does not depend on size of the system anymore. So if we use local heat transfer coefficient, Nusselt number here will be local Nusselt number as well. In this case, if you move D over K to the other side, you get Nusselt number to be 48 over 11. Okay? So for this particular forced convection problem, okay, with constant heat flux, Nusselt number can be calculated simply by 48 over 11. But we just discussed that local heat transfer coefficient is not quite useful. In order to do macroscopic balance, we need either arithmetic means heat transfer coefficient or logarithmic means heat transfer coefficient. All right, so we do not want this one. Instead, we want Nusselt number A, Nusselt number log mean. The other one, to be complete, is Nusselt number using inlet temperature difference only. Of course, this one is not very useful, but I am going to use this one because it is easier to do the calculation. These two are very complicated. So just to show you the concept, in this case, I want to calculate this part. Okay? All right. Now, we already found wall temperature, equation representing wall temperature. Okay? So if I apply this equation at the inlet means at Z equal to 0. At Z equal to 0. When Z equal to 0, it means A is equal to 0. All right? But this is a stretch. Remember, we said that temperature profile that we obtained was calculated at very long length, not at very beginning. But we will try to stretch that equation to be used at the inlet to see how the solution would be. Okay? So, if you replace A equal to 0 here, you see that my T wall would equal to 11 over 24 Q0 R over K plus T1. Of course, this one is wall temperature at the inlet, so I'm going to call this one T01. 1 here means at inlet. All right? And then we know that if you check bulk temperature equation, we already found the bulk temperature equation. TB would equal to T1 plus 4a Q0 R over K. Okay? So at the inlet, or at Z equal to 0, at the inlet, A is 0. I will get T bulk at the inlet to be, A becomes 0, that would give you T1. Okay? According to our system specification, the inlet flow has temperature of T1, so this one is T1. That means even though my temperature profile was obtained when Z is very long, but it's still useful, it still gives you correct answer at short distance. So it's not quite good. All right? So if I take this part, equation 1, and this equation 2, these two should give you the difference in, this is driving force. So if I get T01 subtracted by TB1, which is wall temperature at the inlet, and bulk temperature at the inlet, this is driving force at the inlet, that should give this subtracted by that, T1 would cancel out. You get 11 over 24 Q0 R over K, or 11 over 48 Q0 D over K. In the same manner as what we obtained for the local heat transfer coefficient. All right? So this side of the board will be local. This is local. This side of the board will be macro. Okay? In order to do macroscopic balance, we need to find overall heat. Because according to the definition, Q total equal to HA delta T. This is definition, okay? If I use H1, which is inlet heat transfer coefficient, this delta T is supposed to be the difference at the inlet only. Remember, this one does not make any useful sense, but I'm going to use this one because the calculation is simple. So this one will be T01 subtracted by TB1. This is definition of overall balance using this H1. If you change this H1 to HA or H log mean, this one will be delta TA or delta T log mean. All right? This is by definition. So in order to get this H1, I need to know Q. How do I get Q? So let me erase this part. So in order to get Q, basically it is double integration of the small flux. This is constant flux, right? You integrate it along the length, and around the circumference. So when you integrate it around the circumference, you need R, according to calculus, dr, from 0 to R. I'm sorry, not, you integrate it around the circumference, you need to integrate it with respect to zeta, from 0 to 2 pi. Okay? And you integrate it along the length, that's dz, from 0 to L. And you see that this is constant according to problem statement. You can move it away. The rest should give you Q0, 2 pi RL. Or you can say from the very beginning, it is constant, multiplied by surface area, the area that is heated, that will be circumference times length. That's 2 pi times L. All right? And this Q0 was calculated from here. Okay? So if I remove everything else except Q to the other side, I will get Q0 to be 48 over 11 K over D times T01 subtracted by TB1. That's Q0 multiplied by 2 pi RL. That would be my total heat transfer throughout the pipe. So now if I move this to that, so this part becomes 48 over 11 K over D T01 subtracted by TB1 times 2 pi RL equal to this H1A T0 subtracted by TB1. And note that this area is total heat transfer area, which is 2 pi RL. All right? So 2 pi RL here and there cancel out. This delta T cancel out. You eventually end up with H1 equal to 48 over 11 K over D. Or Nusselt number at the inlet point, or Nusselt number based on inlet temperature difference would equal to 48 over 11 in the same manner as what we found locally. This is coincidence, not actually coincidence. If you do the calculation for arithmetic means or logarithmic means, you get other number. Okay, but you see that in order to find arithmetic means or logarithmic means, you need to do the mean average, and temperature here is no longer T0 minus TB1. It will be arithmetic means or logarithmic means, which will be a little bit complicated. So the concept is that you can do the macroscopic balance and still get Nusselt number based on that. All right? So let me wrap up again. This is the end of chapter 14. In chapter 14, we just want to use the temperature profile that we obtained from chapter 10, 11, or chapter 10 and 11, and try to come up with some variable that is useful for do macroscopic balance easily. That variable is heat transfer coefficient. All right? And now we said that once we define heat transfer coefficient, how we can get that from temperature profile, I show you from using these examples. All right? That's the end of chapter 14 and also the end of the energy session. Next time we will move on to mass transport. All right? And it would take maybe 8 lectures to cover the whole mass transport thing. All right? See you next time.